Hello classes, how's it going? All right, so today I just want to review a couple of the homework problems from the modeling exponential and logistic functions. You see I even made a little presentation here just to kind of expedite things. So yeah, apologies for not getting back to those of you who asked me questions on this sooner. It's just kind of it's a little bit of a process to get this all set up. But anyway, let's get going. So the three questions that were asked were 45, 46, and 50. So we'll start with 45. So this first one is using a logistic growth model to represent the spread of flu after T days. So they want to know. By the way, most of you had questions on parts B and C. So part A, that's good that you get that, and then of course I'll show you parts B and C. So it says, okay, what was the initial number of infected students? Well, when they say initial number for something, that means that that's when the amount of time that has passed is actually zero, no time. It's at the beginning. So if we're going to let t equal 0, so t equals 0, that means we're going to evaluate p of t, which turns out to be 800 over 1 plus, and then that's just going to be 49. 49 times e to the 0, so it's going to be 800 over 50, which is 80 over 5, which I believe is 16. I checked that out earlier. Let's go 80, there it is. Divided by 5 is 16. Perfect. So 16 people were infected. Great. Now the next one's a solving. It says, when will the number of students infected be 200? Okay, so the infected students, this is how many people are infected, right? After so many days have passed, that this function outputs how many students are, have the disease. So, all right. So we want to, since we don't know how to set this equal to 200 and solve yet, we need to resort to graphing. So here's the graph of the function. Okay, this models, again, the flu at that particular high school. Now, of course, we're looking at 0 and our negative numbers here. So that's kind of weird because we have negative days and how many kids. I guess this would be speculating how many kids had it before they started measuring. But so as we know, on day 1, we're at 16. This is accurate, right? You can see t equals 0. That's the y-intercept. Now, as we're looking at this too, I mean, this is nice to have it on a touchscreen. I can kind of pan in and out real fast. You can see that it looks like an exponential growth function, but one of the things I mentioned in a previous lesson, and you may have heard elsewhere, is that exponential growth occurs, uninhibited just for a short period of time. But after enough time has elapsed, ultimately you run out of resources, in this case, population of the school, and you hit a maximum value. So it seems like the maximum capacity for students at this school, the maximum number to get it could be 800. Otherwise, there's no other people, I suppose. Anyway, so that's just what's being modeled by this function. And if you were on your TI-84 calculator, I would just go to the window. This is the equivalent. And let's look at some real life values, like the feasible domain for this problem, right? The actual values would be starting at 0 days, and we'll just take it to 50 days. And the outputs, the number of infected students, would start at 0. And let's take that let's go up to 850, since we know 800 is the maximum value. So there you go. And then you get a much more clear picture for what's occurring with the spread of the flu at this particular high school. Now the question that they asked is, when does the infections, like the population, the number of infected students equal 200? So we can just go over to here and say y equals 200, and let's see where the two functions intersect, right? Like, when is the population 200? After 13.966 days that we hit 200. 13.966. So t equals 13.966, or let's just basically say 14 days. Okay, and it says the school will close when 300 of the 800 student body are infected. When will the school close? So maybe you should take a second and try to get this one on your own. So again, we're solving for t here. We don't have an algebraic way to do that yet. Some of you may remember how to do that. I'm going to go over that in a future lesson. So same deal. We're gonna take the function p of t and set it equal to 300. So we want to know when it equals 300. So we can go back to our graph and look at, instead of y equals 200, let's look at y equals 300. So if the flu does continue to spread according to this model, after 16.9 days, we're gonna have to close down the school. So 16.9. So t equals 16. We'll just say around to 17 days. All right. So there you go on that one. Let's move on to number 46. So we're going to look at some deer population. So let me jump into Desmos problem number 46. Wonderful. All right. So first one, this is a very similar problem. Since this is just the population of deer, like a growth model here. It's logistic. You can see that numerator, that's our carrying capacity. That's going to be the end behavior model. Y equals 1001. So that's the maximum population for the deer population. It doesn't actually, theoretically, it really doesn't reach that. It just kind of flattens out there. So anyway, so what was the initial population? Just evaluate p of 0. Plug it in there. It's going to be 1001 over 1 plus 90 equals 1001 over 91. Whoops. 91. It's going to be 11. So we started out with 11 deer. So the initial population was 11 deer. When will the population be 600? So let's go over to our graph. Maybe you'd want to try this. So right now, again, this is not looking at a very realistic view. We're not really looking at the axes the same way we would like, that would give us an accurate picture for the deer population growth. So we should go to the window settings. If you were on your TI-84 calculator, just go to your window after you plugged in the function and go 0 for X, and I don't know, let's go to 100 days or something. 0 for Y, because we have just 0 deer we'd like to start with, and we know that we go up to 1001, so let's go to 1100. Again, that's a pretty nice picture. So when do we have 600 deer? How long does it take? If I've been saying days, it's not days. I'm pretty sure this is years, right? T is after T years, yeah, because they don't they don't replicate that quickly. Okay, so we want to know, we want to graph y equals, the output equals 600. So you can see here that after 24.5 days, you should have, years, you should have 600 deer. 24.5. So T equals 24.5 years. What is the maximum number of deer possible in the park? We talked about that at the beginning, actually. The maximum number would be 1001. Again, based on the number of resources at the park, eventually, the deer they would just stop propagating, or they would just level off. They'd be making more deer, but also I guess they'd be dying at an equal rate, and they'd be probably running out of food. All right. This last problem. So this one's a little bit tricky because they ask you to flip back to section 3.1, and if you don't have a book, you just would have had to have opened that PDF. When I assigned the problem, I didn't look that closely at the fact that they were referencing 3.1. I saw them reference the chart, so I thought they were just going to be asking questions about that. So this one is I'm going to do with the TI-84 graphing calculator. So let's do it. So it says using table 3.14, compute a logistic regression model for Arizona's population for T years since 1900. Now this is something that I should have done with the other examples that I gave in that previous video. Instead, I just literally used the number like 1900 as a year. And everything worked in my tables, just the numbers were really big and it made the coefficients super small. And I don't know, it's like I just was caught up with the production value or whatever of the video. I just wasn't thinking just start at year 0 and then state that the first year is 1900 or whatever. So I would say that when we make our table for this, right, you see the table that they gave us here, right? When I go to the table in the calculator, we go stat and edit. I already entered all these values. I start at year 0, that represents 1900. Year 10 is 1910, so on and so forth. When you do that, the coefficients tend to be a little bit nicer. The carrying capacity will be the same if you had left it as 1900, 1910, 1920. But this is definitely a little bit, I would say it's a little bit nicer. So so they want us to make a logistic regression model for Arizona's population for T years since 1900. Okay, so let's do that. We have that going on, and then so we have all the data in. Wonderful. One thing I would like to do is turn on stat plots, so we can get that on there. So y equals, second, y equals, you go to stat plot. Let's turn that on, and make sure it's referencing list 1 and list 2. We're good. And then we can look at our y equals. Now, one thing you're going to see when I go to y equals is under Y2, I did plug in the next part of the question. They want us to compare the model to the population growth model in problem 56 from section 3.1. So I brought problem 56 over to here so we can look at it. So P of T is equal to 19.875 over 1 plus 57.993 e to the blah, blah, blah. Okay. But this is interesting. They say where P is the population in millions, same, and T is the number of years since 1800, not 1900. So that does kind of throw a little bit of a wrench into this situation, just because we just plotted data where the year 0 represents 1900, and this function's year 0 represents 1800. So we're going to have messed up results here. So, but anyway, I'll talk about that in a second. But Y2 is just that. Y1 doesn't have our function yet, the regression function. But when we go to graph, you're going to see that's the data that we have. Okay, so we want to come up with a model. So we'll go back to stat. We're going to compute a logistic growth function. L1's our x list, L2's y list. We're going to store the regression model in Y1. So if you recall, alpha calc or alpha trace, takes you here. You pick the y value where you want to store it. So that's good. Calculate, yes, it's doing our logistic growth. Great. If we go look at y again, we have y equals 15.64. So let's write that answer down. It's going to be population, I'll call it for Arizona PA, relative to T, is equal to 15.6415 over 1 plus, let's keep going. All right, so you have some scientific information first on this one too, 156.289, actually no, there's no scientific information, 156.289, e to the negative 0.04, 3249. Okay, so that's that function. Now, we could pretty much answer this question right now, just by even looking at the two functions, because I'm going to highlight this numerator, I'm going to highlight this numerator. The question is, based on your model and the New York population model from exercise 56, will the population of Arizona ever surpass that of New York? If so, when? So actually, I would say we're pretty much done here. I mean, I am going to graph them both in a second, but yeah, I mean, we know that the answer to that question is no, because the maximum population for Arizona, according to this model, is going to be 15.6 million, right? Whereas the maximum population for New York is closer to 20 million. Okay, and again, that's maximum, so there's no way it could even possibly pass it, just because there's not enough, again, probably not enough resources in Arizona to support that kind of population, at least now. All right, so if you want to stop there, that's fine, but I am going to just finish talking about something that's slightly more advanced. So when you look at the graph of this function, you can see that would be, the continued growth according to, the current data that we have. If I want to compare that, I want to look at it on the same set of axes next to New York. I need to shift New York's this function over 100 years, right? Because we were talking about number of years since a certain date. So the New York function, well, it does include 1900 as well. It's because its starting time is 1800. So since the Arizona graph starts at 1900, we need to take y2, which is New York, and we need to shift it. So there's actually a fast way to do that using transformations, using function notation. I can go alpha, trace, and for y3, I'm actually just going to graph y2. But I'm going to take its argument, I'm going to say, take my function and shift it 100 to the left. So now that's going to show me y2, but making so that if I were to plug in 0, the first year is going to show me 100 plus 1800, which is 1900, right? So now when I go to graph that, I can see New York's population on the left, and then Arizona's population on the right. And you can see we haven't even quite hit our carrying capacity yet for either of them. So even if we wanted to go further on to the future, because right now I'm only starting at 0, 1900, and going out 200 years from there, we can go out 500 years and take a look. It's a little bit more steep there. But you can still see that the black graph there, that's New York, that's... it's almost like they're essentially running parallel, right? Their end behavior models are horizontal lines. It's always going to be quite a bit higher. So anyway, hopefully you found that last part a little bit interesting. And let me know if you have any more questions.